Welcome to 4.1, Graphs of Polynomial Functions. So, polynomial functions are continuous, smooth curves with no corners, with a domain of negative infinity to positive infinity. So, we have the generic polynomial function. We'll call it p of x for polynomial, where we start with some coefficient of some power, and then again, as you see the n minus 1s, we're just saying the powers are slowly going down until we end up with a constant term with no x value. Okay, so some vocabulary. We have ax to the n is the leading term or the leading coefficient. An is the leading coefficient, n is the degree, and a sub 0 is the constant term. And then we have some important functions that are going to be the main ones we'll look at. So we have the constant function of degree 0, it's just flat. Linear functions like lines. Slanted, there is no curving to it, it is straight. We have quadratic, again, like a parabola. Then we have cubic functions. Goes like that. Then we have degree 4, a quartic function, usually just, I say, degree 4. Then we have a quintic function, or degree 5, like that. Okay. So example 1. State A, the leading term, B, the leading coefficient, C, the degree, and D, the constant term. So for A, the leading term, again, highest power 1, the leading term is going to be the negative 9, or negative x to the 9th power. Then B, we're talking about the leading coefficient, and the coefficient is whatever's in front of the leading term. There's a negative, but again, that's going to be a negative 1. Then the degree, well, the degree is the leading term degree. We just ignore the other degrees, so it's going to be degree 9. And lastly, our constant term, the one hanging out at the end, is negative 8. Again, the one that doesn't have a variable will be your constant term. So, the number of turning points. The number of turning points for a polynomial of degree n greater than or equal to 1 is at most n minus 1. So how many times when we graph our item that it turns or changes? So my n in this case, n is going to equal 32. And then let's see my turning points is going to be n minus 1, which in this case is going to be 32 minus 1, which is going to be 31. So the maximum number of turning points is 31. So you just take your highest exponent and then subtract it by 1. Now let's look at some things called extrema, or extreme values, minimums, and maximums, highest or lowest numbers. Note, the value of a function is the y value p of x. So if we're talking about the value, we're talking about y. And if we're talking about a point, again, it's the point. So some small verbiage there you got to keep track of. So we have a few differences. There's absolute and then local extrema. So absolute max and min, and then local max and min. So P of C is an absolute maximum if it is the greatest for all of those values. So a maximum, an absolute maximum, in this case, it would be whatever point that is right there, because there is no other point that's higher than that. Now, an absolute minimum would be a point that has no other points lower than that. In this case, we don't have an absolute minimum because our points go on to infinity. There is no absolute minimum. Okay, so we don't actually have one. Now, a local maximum would be one in the area where it is small. So a local max would be, for example, this one. It's a tall one for the area. It's not the absolute max, though, because the absolute max, again, was this one. Now, a local minimum is, again, a small value for the area. The small one, for example, is that. That would be a local minimum. However, it is not the absolute minimum because, again, the absolute minimum would be the smallest possible one, which we don't actually have because these arrowheads go down to infinity. For example 3, for the polynomial f, give all local extreme points. State whether each is a local minimum or local maximum. And then, are there any absolute minimum or maximum values? Alright, so let's take a look. Let's go ahead with a local min. And we're talking about points. So careful here again. Points is when we're going to talk about an xy point. If we're talking about a value, we'd be talking about a y value, as mentioned above. So let's see. Some local minimums. We have this one. Oops, let me change to a highlighter. This local min and this local min. So let's go ahead and write those local minimum points. -1, -3, and 4, -1. Now let's take a look at any local maxes. And again, we're talking about points. So we'll use the point coordinate set xy. So maximums. Well, local max here and here. Now, are there any absolute minimum or maximum values? Let's see. Absolute minimum? Oh, what do you know? We have that arrowhead. That goes down to -infinity, so we don't have any absolute minimums. So our answer is going to be none. And then, any absolute maximums? Well, let's take a look, and oh, again, we have that arrowhead. So there's not going to be any absolute maximums. So again, we're going to have none. Though we do have some local ones, we don't have any actual absolute max and mins. Now, for example 4, for the given graph, state any absolute minimum or maximum values this time, not points, we're talking about values. So again, we're going to be talking about y points. And then B, state any local minimum or maximum value. So again, we're talking about y values. First off, let's go ahead and make note of where we have our curves changing. So this point here is one of them, and that's at -2. Let me write that out. -2, -4. Then we have another curve change here at 2, 0. And then another curve change here, I'm going to approximate to 4, -1. So again, we always have our max or mins at that curve change where it changes something like that. That's going to be where our max or mins are going to be located. Now let's see, any absolute minimums? Ooh, we do. Right here at this point, we have an absolute minimum. That's the lowest possible one around. Not even around, that's the lowest possible one for my graph. And the y value is -4. Any others? No. Again, usually you're going to have only one absolute value. And then any absolute maximum value. Well, again, we're talking about the y's. We have these arrowheads, so we're not going to have any absolute max values for y. So again, my answer would be none. Okay, we're done with the absolutes. Let's take a look at any local. Any local minimum values? Yeah, we had a local min right here. That's going to be at, remember the y value? We're talking about a y value, -1. And how about any local maximum values? So any local maximums, let's see, that's going to be at, right here, maximum value, y value of 0. So because we're also just talking about local maximum for the area, we're also going to include the -4 for a local minimum as well. All right, so moving on, let's take a look at some end behavior. So as our x values go to -infinity or +infinity, we want to know what's happening to the y values. For linear functions, our y values go up or down for degree 1. For for quadratics, degree 2, notice they both head upwards. For degree 3, one heads down, the other heads up. Degree 4, they both again head upwards. And degree 5, one down, one up. So you'll notice the odd degrees have one up and one down. Even degrees have both up. But again, that's going to change if we have a positive or negative coefficient for a leading value. So let's take a look at the definition from the book. So the end behavior of our polynomial is determined by the degree, n, and the sign of the leading coefficient. So if our polynomial has an odd degree, two options. If we have a positive leading coefficient, it'll go in this direction. If we have a negative leading coefficient, it's going to head downward. For example, if I was looking at positive x cubed versus negative x cubed. Then if we have an even degree, if the leading coefficient is positive, both of them are upwards. If it's negative, both are downwards. And for example, positive x to the fourth, both heading upwards, negative x to the fourth, both would be going downwards. So we're going to go ahead and describe the end behavior using one of these diagrams for describing. And again, all we're going to do for describing the end behaviors is look at the leading coefficient and the degree. So this is an odd degree and positive leading value. Okay, so we have a positive leading coefficient. So odd degree, positive coefficient, how is that going to end up being? Like this. One down, one up. Next, for B, we have a negative, we have an even degree. And then we have a negative coefficient. So even degree but negative coefficient is going to be going downwards. And for C, now we have an odd degree and we have a negative coefficient. So odd degree, negative coefficient, it's going to be heading this direction. And then, half is still positive, so that's okay. So we have 10, which is a positive or an even degree. And then we have a positive coefficient. So even degree, positive coefficient is both going to be facing upwards. Now, next we're going to take a look at the x-intercepts or the real zeros. So when we're talking about zeros, we're talking about x-intercepts. And the number of x-intercepts, well, let's see. The graph of a polynomial of degree n will have at most n x-intercepts. For example, if we had x squared, it would have at most 2 x-intercepts. So for this one here, state the maximum number of real zeros. Well, again, we're going to look at the highest exponent that we see, which is going to be 112. So that would mean for this specific one, the maximum number of real zeros would be 112. Okay, again, just based on the degree, the maximum degree, or the highest degree that you see. So next, for example 7, we're going to match each polynomial to its graph. Again, how do we do that? How do we match it? We're just going to look for the end behavior. And again, the end behavior is based on positive or negative for the coefficient, and then if it's even or odd for the degree. So for p of x, it's a positive 4 and an even 6, which means the end behavior should look like that. For the next one, we have a negative 2 and cubed. So it's a negative coefficient and a cube or odd degree, which means we're going to be looking for that, for the end behavior again of our graph. And then for this, we have a negative but an even degree. So negative but even degree is going to be heading downwards for both of them, for the end behaviors of our graph. And lastly, we have a positive coefficient, but an odd degree, which means the end behavior is going to look like this. So let's go ahead and match this up. Which graph has 2 upward facing? Well, that's going to be C. Which graph has up and then down? That's going to be D. And then which graph has down and then down? Going to be B. And lastly, down and then up, which is going to be A. So I'll go ahead and label them that way. This is going to be graph A. And then the next one is going to be D. And then let's see, C. And lastly, B. And there we go, an easy way to sort of just figure out what your graph would kind of look like based on the leading coefficient and again the degree of our leading term. Alrighty, that is it for this section. If you have any other questions, please send me an email.